slides for today, and I'm like, I don't think that's 50 minutes worth of slides, but we'll see how long it takes. How long it takes is how long it takes. We're not going to start the next unit of material. Oh, come on, go forward, please. It's frozen on a blank screen. Come on. Oh, there it goes. Okay, that's better. So a little before, we talked about work. Like, remember we had the guy moving the crate, and he was going to apply a force, and the amount of work he expended is equal to the force he applied, and times the distance over which he relocated that crate. Okay. Well, we're going to talk about now. I get my verticals and horizontals mixed up. Okay, but that was more like horizontal motion. Relocating. We're going to talk about something kind of more like vertical. Simply, if we are going to relocate an object against the force of gravity, it sounds so dramatic, and you can pick out however heavy object you want to do, but literally, if I put this on the floor and I lift it up, I'm working against gravity. Now, whatever force is required to relocate, and I could make a more and more massive object, okay, whatever force is required to relocate that object is equal to the mass of that object times the force of gravity. And the force of gravity actually, I shouldn't say force of gravity, full of force of gravity, but we're going to use that acceleration due to gravity, lowercase g, okay? And so what's the value of g? To 2 digits. 9.8. Yeah, and units are meters per second squared. 9.8 meters per second squared. That's what the little g is. Okay? Okay, so that's the force to relocate an object. Okay? A force I need to apply. Now, we said in the earlier thing that work is equal to force times distance, and it's a similar thing. Work accomplished here is going to be equal to force, which is the mass times that 9.8 meters per second squared, times the distance we relocated. And instead of d, we're going to use h because we're going to do a height sort of thing. So that's why we have the mass it is times that 9.8 meters per second squared times the height over which we relocated. Okay, that's it. That's the work that's accomplished. And we talked last time where, by the way, what units are working? Do you know? Could be calories or could be joules. Exactly. Yep. So these are joules that is expended. These are joules work accomplished, and then energy expended is equal to the same thing. Okay, so work accomplished, energy expended are equal to the same thing. Okay, so we're going to do some problems. You know how that works. And again, I know your homework's been throwing like kilometers in at you, kind of some different sort of units, but on your exam, I'm not going to make you convert to something. I just want you to use those little formulas I gave. Plug and chug is what they say. So here we have these books have been relocated to a certain height. Okay, stack of books with a mass, which would be, remember the mass is the same on the moon or on Earth, but the weight is different. A mass of 9.07 kilograms, okay, and that they have been relocated to a height of about 5 feet, which is 1.52 meters. So it's funny because I said the kilometers were always going to, I'm always going to give you meters, but now kilograms actually is the base unit. So kilograms, we're ready to go. So here we go. We're just basically going to plug and chug. Let me see if my stylus is working this morning. So of those things I gave you, oops, come back. Of those things I gave you, we're going to use the W is equal to mgh. Sometimes I say, don't make it harder than it is. Okay. Oops. Oh, you are so silly. Okay, good. It's working. A lot of times, I guess I would encourage you, if it's homework problems or if it's a problem on the test, go ahead and hit me over the head with it. Go ahead and say, this is what I'm going to use, and here I'm going to use it. So you can't go wrong with saying that. So if we go back up to the problem, what's the mass? Yep. 9.07 kilograms. Perfect. And what's G? Yep. 9.8 meters per second squared. Perfect. And then what is H? 1.52 meters. Perfect. And as long as we are metric, which we are, again, don't let the kilograms, don't let the kilo and kilograms throw you off. That is the base unit. Kilometers, not base unit. Kilogram, yes. So we have units of kilograms, meters per second squared, and meters. We are good to go. We are golden. So we're going to round. Our calculator is going to display something. Let's go ahead and see what the calculator displays. Times 1.52. So what my calculator displays is 135.10672. And what would these units be? Joules. Perfect. You got it. So as far as digits, I've got 3 digits here, 2 digits here, and 3 digits here. And we're always, what we say, conservative. So I'm only allowed 2 digits. And again, I'm not going to really give you a hard time with your homework or on a test if you go ahead and give me 135. But honestly, we go from left to right. I'm going to keep this digit, and I'm going to truncate it right there. I'm really kind of not allowed that 3rd digit. So if I'm only going to give me 3 digits, is it going to be 130 or 140? 140. We just generally round up if that's a 5. So 140 joules. Now, sometimes students will, and I kind of understand this, they'll say, oh, Mrs. Snipes, I kind of get that 2-digit thing, and I'm going to keep the 1 and the 3, and then they write down the number 13 or 14. And no, you have to go ahead and bring that, include that. That's it. One of the things we talked about before is if you take a joule and dissect it, can you kind of see here what the units of joules would be? I get so excited about units. So another unit for joule would be kilograms, meters per second squared, and then we pick up another meter here. So actually, units of a joule, if you break it down, it's a kilogram meter squared per second squared. It totally is, and that's actually one of the things we talked about before. All right. So a related question is how much, I'm going to kind of see if I can do this, how much work is done? Let's see if I can. What do you guys think? Can you just shout out an answer here? How much work is accomplished? Or sorry, how much energy is spent? This is work accomplished. So how much energy is spent? 140. Yep. Work accomplished is equal to energy that was spent. So, I don't know, say those books have been there. If it's like me, I don't read as much as I should. They've been there for decades. Okay? So decades ago, somebody spent this much work, energy to accomplish that much work. Good for them. So this homework will be due next time we meet Friday. Friday, I definitely will go ahead and bring the 4th part of physics here. handout. So page 106, exercise 4. So, and I'll kind of, I think I've got it. I'll be able to throw together a review sheet for you for your unit exam on physics and all of your unit exams, just to kind of give you hints what's going to be, you'll maybe run into on your exams. Now remember, your exams won't all be problems. Some of them, the questions will be more like other things we talked about. Multiple choice section, short answer section, and a problem section. All right. Yep, somebody said PE is potential energy. It totally is. So potential energy is stored energy. Batteries are an example of potential energy. A candy bar is an example of potential energy. Okay, it's just itching to can be turned into energy that's on the move, which we call kinetic energy. Now, one form of potential energy actually has to do with the distance that something can potentially drop. And I think I mentioned the other day, for instance, if I put an object on the edge of the table, okay, you can spatially see that object can fall. Okay? So it has a certain amount of gravitational potential energy. I can scoot it over and I let gravity do its thing, and I probably shouldn't because I've already had technical difficulties today. The whole PVs and everything. So anyway, I could let gravity do its thing, and then that potential energy would be turned into kinetic energy for just a little bit, and then it would fall to the floor. And with regard to falling off anything, at that point, unless I dig a hole, at that point it has zero potential energy, or zero gravitational potential energy. Okay, here it has a certain amount of gravitational potential energy. So with regard to an object's location, we kind of say its potential energy is equal to the mass of the object times that 9.8 meters per second squared times the height that object can be relocated. That's potential energy. So if this looks familiar, it's because we just saw it. We said that work accomplished or energy expended is equal to, if you're relocating the object horizontally, the mass of the object times the 9.8 meters per second squared times the height over which you relocate it. Same thing. So we're just kind of looking at it differently, which can be good or bad. Okay. So we're going to do one of these, potential energy. So like, how much potential energy does an apple have? As long as we know the mass of the apple and the height over which that apple can drop. So it's going to feel very familiar because it is very familiar. So I'm trying to think. Yep, on that sheet I gave you, by golly, I do have the work is equal to mgh. We're talking about vertical work. And I have potential energy is equal to mgh. So here we go. I think it's pretty good if you restate the equation you're using. PE, or potential energy of the apple, is the mass of the apple times the acceleration due to gravity times the height over which that apple can fall. So potential energy, I'm just going to go ahead and grab the mass, 0.14 kilograms. My G is going to be that 9.8 meters per second squared, and the height over which it can potentially fall is 1.2 meters. Be careful, little apple. So how many digits am I going to leave in my answer? Just 2 digits, yep. So 0.14 times 9.8 times 1.2. And I'm going to say what my calculator says. Well, it doesn't say anything, but what it displays is 1.6464. I think I might have it. Yeah, anyway. What will those units be? They'll be joules again. Yep. So 2 digits. I'm going to truncate it right here. So what's my answer? 1.6 joules. Never forget your units. I'll give you a little bit of a pass with the units working from, but I don't know. I feel like I'm emphasizing it enough this semester. So you should always include units as you work it, and for sure include units at the end. That's it. That's it, man. I meant to print these out. Let's see. Dun, 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 dun. So I've got 2 of these. Well, go ahead and, you've got calculators, do a problem. Is it not in your notes, right? Okay. So you just I get 2 weeks. This is the first 2. Problems up. Okay. So again, we have an apple, and its mass is 1.31. What's that?
Where do you want to just write down on this one?
Sure. Wherever you want to do. And the distance is given. So what's its potential?
After I liked it.
All right. Oh, I might do that again. All right. So potential energy is stored energy, and kinetic energy is energy associated almost with motion. Okay, so I think of kinetic energy as being spent energy. And there are a lot of things in this universe that are conserved, and energy is one of them. But energy oftentimes quite easily goes back and forth between kinetic energy and potential energy. So just a minute ago I said I can have an object here, it has potential energy, the amount of when it's falling, it has kinetic energy, and when it's back at rest again, basically had no potential energy, I said, with regard to its ability to fall. So in that case, all of its potential energy was converted to kinetic energy just over the time in which it fell. Okay? So they're showing a rock doing the same thing. Okay? So as potential energy decreases, kinetic energy increases until it hits the ground. And then we could talk more about this, but like on a small level, oftentimes if you had a thermometer there, you might even like see a little bit of heat increase. So it's kind of a transfer of energy. The ground might shake depending upon the size of the thing you dropped. You had an earthquake the other day, didn't you? But anyway, that's a type of energy too. Sound might happen. But if things are conserved, that means if you add them together, they should be a constant. And that's kind of what it's showing there. The total amount of energy. You can see this didn't make it to your equation sheet, so we're not going to spend a whole lot of time, but it might be a concept. The total amount of energy, if you're talking about kind of back and forth between kinetic and potential, has got to be conserved. It's a sum, or the adding the two together. So this is a pendulum. No, this pendulum does not have 5 little balls. It's showing you the pendulum in 5 different positions. Okay. So if you think about a pendulum, when it's up here, okay, how much motion does it have? 0. When it's kind of in the middle of its swing. So 0 motion actually means 0 kinetic energy, but it has a lot of potential energy. Where's its fastest? It's 0 here and 0 here. Where's it fastest? The bottom of the swing. All right, the bottom of the swing, with regard to potential energy, your height is the smallest. So we have the most kinetic energy here and the least amount of potential energy. So as it swings, you could at any moment, it's kind of fun, you could add up its potential energy plus its kinetic energy, it will be constant. So there are so many different things that matter is conserved, energy is conserved, just in general. Cool. Switching gears to something you guys are going to do tomorrow. If you read your write-up, which I encourage you to do for tomorrow's lab, basically, I laugh because I don't have to do it. You guys are going to be going, let's see where we're over here. You know that ramp that goes kind of over by the computer lab? Goes up. Okay. You're basically going to be carrying books. Okay. So you have a certain amount of work that's going to be accomplished as you relocate those books up a certain height that the ramp allows you to do, and you're going to do it over a certain amount of time. If we take work divided by time, that will give us power. It's way fun. So if work, the power is work divided by time, and work is joules, right? So then power must be joules per time. But actually we introduce another unit, okay? We introduce this capital W is not work, that capital W is the watt. You would think they could be a little more clever with some of the variables they come up with. But that is the watt. Okay, so a watt can be equal to, like I said, a joule per second. Or if you go back to kind of the base units, it gets awesome. A watt can also be kilograms, meters squared per second cubed. How fun is that? But watts are usually like if you go out and kind of look at your meter spinning around, an electric company will talk about in terms of watts that you've used for the month. So let's do another example. Looking at power. So in order to calculate power, we need to know the work, okay? And in this case, we've gone back to this dude pushing on a box. He has a force that we know. We have the distance that he relocated this object. So from the force and distance, we can get work, and then we just got to divide it by time. So, let's work it. Now we could do it a few different ways. How do I want to do it? I think I might work it this way. Let's go back to a problem. We said work, and he's doing this horizontal work is equal to force times distance. So I'm going to plug in the force. The force is 4.5 newtons. And again, I am going to be looking in the homework and in your on your test questions for you to put the units times the distance, and the distance here is the distance here is 0.343 meters. Okay, it looks like I got 2 digits. My calculator displays 4.5 times 0.345. My calculator displays 1.5525 units of work. So we're going with joules, right?
I got 3.
Really?
No, 5, 4, 3.
Oh, wonder if I have the wrong. Yep. Thank you. I have the wrong. I got sloppy. 4.5 times 0.345. 0.343. Final answer. I got 1.5435. Cool. Good. Thank you. Ugh. 0.5435. So I'm going to go with 2 digits. And with 2 digits, I'm going to truncate it right here. So what's my answer going to be? 1.5 joules. Well, that's not my total answer, but that's my work term. So I broke it up this way. You wouldn't have to, but I am. This time anyway. So my power is equal to work divided by time. I'm going to take my work, 1.5 joules. Again, use units if you want to get all the points. Divided by time, which is 34 seconds. 1.5 divided by 34. This is where sometimes in working science, working problems with numbers, we're like, well, I could use the unrounded value and get a little better answer, and you really could. So I could take either way, but I'm rounding it. I'm going with my rounded value, 1.5 by 34, and I get what my calculator displays. Is this what yours displays? 0.00. Oh, sorry. 0.044176. Blah 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 blah. Units would be what?
Joules per second.
Joules per second would be awesome. Or watts. I'd take either one. So we're going with 2 digits. So this is where, I'm glad we're having this conversation. So this 0 doesn't count as one of my digits. It's a placeholder. So I'm going to actually go, that's a digit, that's a valid digit. So I'm going to actually put my truncating there between the 4 and the 1. So, and since this is a 1, I'm going to leave it the same. So your answer here is 0.044 joules per second or watts, either way. Work? So let's see. We're going to take it up a notch or change it up a little bit. If you can read through my writing there. We're going to take the force, and the distance is the same, but we're going to cut the time in half. Okay? So if you cut the time in half, just intuitively, what do you think? Is the power going to increase or decrease? How many people think it's going to decrease? How many people think the power's going to increase? So this is why tomorrow's going to be fun, because actually you're going to feel this. Feel the burn. Okay? So, as I say, feel the burn. The deal is, if you accomplish the same work in 17 seconds versus 34 seconds, you're going to feel the burn. So your power is going to increase. The power will increase. If we decrease something in the bottom, which is called the denominator, then that's going to increase your... So, let's go ahead and knock this one out. So I'm not going to redo my work. My work's the same. Okay, because I still have the same force over the same distance. So it's a 1.5 joules divided by now 17 seconds. My calculator displays, come back, 1.5 divided by 17. I got, well, it should be half of that up there, shouldn't it? Or twice that. 0.0088235, blah, 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 blah. Units are going to be joules per second or watts. I'm going to go with 2 digits, so I'm going to truncate it right here. Wait. Oh, sorry. Thank you. I have one too many zeros. So the answer is going to be 0.088 joules per second or watts. Same diff. So we doubled our power by halving our time. This one, I think I'm going to hand out when we meet tomorrow, Friday. Okay? Because I am. So that's how far I wanted to get today. Okay? Any questions? I'll take that just for kicks and I'll bring it tomorrow. Bring it tomorrow. You guys got time? Write this down. Just write this down and hand it in. Or do you want to do it here?
What?
I'm so confused. I know. You see, we still got 10 minutes. So go ahead and do this problem. I'll give you guys assignment points for doing those 2 problems in class. How's that? I know you have to read it a few times. 2 people who weigh the same climbed a set of stairs. First person climbed it in 30 seconds. The second person climbed it in 40 seconds. Which person does the more work? Let's just do it this way. Don't have to write anything down, but you will for this one. I'm winging it. Which person does the more work? Which one? The one that does it in short amount of power. I'm sorry, they both do the same amount of work, but the one who did it in shorter amount of time expended more power, had to take more power. Very good. Does that make sense? Okay. Okay, so you guys did that. So now do this one. How many watts of power is expended by weightlifting 60 kilograms, a vertical distance of 1.2, and a time interval of 1.5 seconds? So power is equal to work divided by time, and work here is equal to mass, or should be gravity. Work here is equal to GH. See if you guys can all get the same answer.